Is it okay? Do you see my screen?
We see, yes.
Good. So hello everyone. As Lionel said, my name is Nathalie Levêque. I am in charge of the investigation analytical team at the NQSC Vittel. And I will talk to you today about PFAS analysis, specifically by targeted analysis, but not only, also by suspected and non-targeted analysis by LC-HRMS. So I will go fast because Stefan did already a very good presentation about the PFAS, but just from this slide, what we have to resume is PFAS we can find everywhere. It's coming from cosmetic, from packaging, from textiles. Well, it's a really we can find in all kinds of household products. So how are we exposed to them? So the human exposure can be direct or indirect. The direct exposure of PFAS for the human, it's from food, essentially. It can be from food and also from the environment. And indirect contamination can come from industry and the waste as well of these industries. Considering the environment, so because at NQSC we are analyzing water, not only, but a lot of water. So considering the environment, we have a different direct source of contamination. It can be from industry, from the waste as well of these industries, but as well from, again, the all household products that we can use every day. So generally, just to speak quickly about PFAS, we can divide into different types. We have the per-fluorinated compounds where you have a complete fluorinated chain. And we have the polyfluorinated compound where you have the carbon-fluorine and carbon-carbon length bond. But not only, you have as well some hydrogen on this kind of chain. I really like this picture because for me, it's really like perfluorinated in water. That's what's happening. So in fact, perfluorinated, you have two different main sites. You have a functional group who can be the head of the duck, and it's the hydrophilic part of the perfluorinated. And you have as well the fluorocarbon tail, which is more the hydrophobic part of these compounds. And that's a unique chemical property, and that's a unique surfactant properties, and that's the reason why we can use this kind of compounds in so many different products. So before, well, at the beginning, we used to speak about the common PFAS, which are usually PFOA and PFOS. But if we look in details, only with these two kinds of compounds, if we look, for example, for the PFOA, we have the linear one, but not only. You can find as well the branch one. So just to let you, to show you that even if we are speaking about one compound, it's in fact not only one, but we have a lot of compounds already. But when we speak about PFAS, it's not only PFOA and PFOS. And there is a very good article that this picture is coming from, where you can find a lot of different PFAS, and you can find more than 4,700 PFAS with a CAS number. So of course, we don't have analytical standards for all of them. So the challenge, the analytical challenge, is how we can detect this PFAS, even if we don't have the analytical standards. So that's a part of my job. It was to put in place a method or methods in order to be able to detect and identify them. So the current state for the analysis of PFAS in water, so the legacy PFAS, in the EPA, we have 61 compounds in the last EPA in regular way in water, and you can also find more than, again, 4,700 PFAS. So at NQSC, we put in place three different screener methods. The first one is the targeted screening. And the question that we want to answer is, are the PFOA, PFOS are present in the sample? So that's specific compounds. The suspected screening, then we put in place a defined list of PFAS. And this suspected list at NQAC, we have 4,777 PFAS inside. And so we look if these compounds are present or not in the samples. And finally, we put in place the untargeted screening. So that means that we completely open mind in the way we are looking for the PFAS. So concerning the targeted analysis of PFAS, in the laboratory, we have already two different methods. The first one is done by low resolution mass spectrometry, which is the triple quadruple. And the other one is the high resolution mass spectrometry, and it is an orbit trap. The two main differences between these two methods is they are the resolution. So with the high resolution, we can detect or differentiate more precisely the different PFAS or different compounds. And that's linked, of course, to the mass accuracy of the mass spectrometer. And thanks to this information, with the high resolution, it's really important because we can as well delete some interferences of PFAS. So by doing this targeted analysis, and especially when we look at the EPA list, so 61 PFAS are listed in the EPA list. And the challenges was to improve the sensitivity of our method, because last year they changed the limit of quantification in water. And now we have a method to detect them and to quantify them down to low the PPT level. So to be able to do that, we had to take care of the blank issues, because as I said, you can find PFAS in everywhere and in the lab. So PFAS are very, it's a complicated method, because you really have to take care of all steps, especially, for example, the dust in the lab, the solvent, the reagents, and the vials that you are using. So it's well known now. So we did that in our laboratory. We put some column delay to separate PFAS coming from the reagents to the PFAS coming from the samples. We used some vials without the PTFE, and so we took care of the PFAS coming from the instruments, because instrument LC-HRMS or LC-HRMS, you can find some PFAS inside, and so we had to change all the tubing by the PIC tubing. So by taking care of these blank issues, this is the two methods that we put in place at NQAC. So with the low resolution mass spectrometry, we are able to detect and quantify 61 regulated PFAS with a very low limit of quantification, because they are lower, all of them lower to 1 nanogram per liter. So as you can see, it's between 0.1 and 0.225 nanogram per liter for the limit of quantification of these 61 PFAS. It is an accredited method, and I would say at the moment, unique application is for water analysis. We also have another targeting method, which is with the high resolution mass spectrometry. So here for the targeted PFAS, we have a little bit more, but among the 86 PFAS, we have the 61 regulated one. And that's, I would say, the bad point, let's say like this, of the HRMS is, unfortunately, we cannot go lower than 1 nanogram per liter. So it can be a problem for water analysis, because with the EPA, we have to be lower than this value, but for packaging, it's absolutely not a problem. So the advantage of this HRMS is to make as well suspected and non-targeted analysis. The problem is when you get this kind of figures where you have all, in this figure, you have the retention time versus the molecular weight of all the compounds we can detect in one sample. So we have to put some rules in order to be more efficient and as well to eliminate the other compounds which are not maybe linked to the PFAS. So the strategy used in the laboratory is firstly to use the exact mass with an error less than 5 ppm. We use as well the mass defect. So what is the mass defect? If you see these elements for example, the fluorine that we are looking for more specifically for the PFAS, we have a negative mass defect, which is the same case for the oxygen, while for hydrogen, for example, it is positive mass defect. So if we look on the mass of the octanoic acid, the mass defect will be positive, while if we change the hydrogen by fluorine, then the mass defect will be negative. So thanks to this first rule, it was possible to prioritize the compounds that we want to interpret by going to interpret the compounds with the mass defect, a negative mass defect. And if you have a very high mass defect in negative way, that means that probably you have as well chlorine or bromine inside your compounds. So that's a first way to prioritize the species to analyze. The second rule is the Kendrick mass defect. So it's another mass defect, but it's a normalized mass defect. And in this graph that I'm showing, it's a normalized mass defect with the CF2 chain group. And what is interesting with this kind of Kendrick mass defect, this time you have the information about the family of the PFAS. So all the family, all the compounds in the same family, so an homolog series, they will all have the same Kendrick mass defect. That means that when you have an unknown compound with the Kendrick mass defect that you already know thanks to other standards, for example, then you can be sure that this compound is part of this family. We have, again, other rules or other tools to help us to identify the PFAS. We have the retention time prediction. I'm not going deeper on this part, but thanks to this prediction graph, we can, again, improve the confidence in the identification of the compound based on the analytical standard that we have in the laboratory. And finally, we have the PFAS diagnostic fragments or specific losses, which can help us as well to firstly be sure that it is a poly or a per-fluorinated compound, and as well to help us to the identification. So here, for example, that's the family of the sulfonic acid, and we have two specific and well-known fragments that prove that with these two kinds of fragments, and of course, all the other rules that I already told about just previously, we know that there are PFAS and there are PFAS of this family. So what is the difference between suspected and untargeted in our laboratory? With the suspected list, you have a specific list with a special number of PFAS. And what we look is, for each of them, we look if there is a mass, a corresponding mass with a peak in the chromatogram, and after we go to the identification. In the case of non-targeted screening, we firstly detect the peak, and after we will go, what is the mass under this peak, and go to the identification if the mass defect, the Kendrick mass defect, and all the rules that I previously presented are fitting. So, sorry. With these three different per-fluorinated screening methods, so for the targeted screening, as I said, we have 86 regulated PFAS. the limit of quantification is around 1 nanogram per liter. For the suspected list, we can see more compounds, but it will be firstly only semi-quantitative work because we don't have an analytical standards for all of them. So that means that we will give a range when we give a quantity. And the limit of quantification will be higher as well compared to the targeted analysis. And finally, for the untargeted screening, you can see thousands of compounds. The limit of quantification can be very different as well to the suspected one. And finally, in the laboratory, we do as well the total organic fluorine analysis. So the good things is you see all the fluorine contained in your samples, but the limit of quantification is higher compared to the LC-HRMS methods. So just few applications. So we did some analysis with different packaging. The two first line are food packagings. So if we use targeted analysis, you can see that for the first packaging, we have detected and quantified around 7 compounds, not around. We have detected and quantified 7 compounds. While when we go to the suspected list, we have much more compounds. So that's quite interesting. And of course, the quantity increase. And finally, with the untargeted screening, again, we increase this number of compounds and the quantity. However, if you look always on this third line, the total organic fluorine is higher than the untargeted screening quantity that we were allowed to quantify. So this gap, that means that we still have a gap. There is something missing, and we have still to work on this part to understand why we don't find the same quantity when we compare the untargeted screening to the total organic fluorine. The last line is another application, just to show you that the method, as soon as it is in place, you can use it for nearly all kind of packaging, all kind of samples. So it's mask that we used in the laboratory. We did some analysis on the mask because of the COVID, as you know. And if we were just doing some targeted analysis, we wouldn't be able to detect none of them because, well, they are not among the 86, none of the 86 compounds are there. However, if we do the suspected and the untargeted analysis, then we were able to detect some PFAS analysis and non-usual one. So that was really an interesting application, but it's just to show you that, again, these methods can be used in different ways and in different samples. So last slide. At NQSE, we have a robust and very sensitive targeting method for water analysis, as we are lower than the nanogram per liter. We have put in place in the laboratory some LC-HRMS methods, and we use especially fragment ions flagging to identify the unknown PFAS. And all these methods are already used and in place in the laboratory for different matrices, water, packaging, and others. Thank you for your attention.